All right. Today, we are going to move on to the next topic of thermodynamics. Last time, of course, we finished up calorimetry, where we talked about latent heat, finishing up the full theory of what it is we need for this particular course on calorimetry, which is placing multiple items into a system, a closed system. Each item may be at different temperatures, and then letting those temperatures come to equilibrium so everything comes up to the same final temperature. And you want to track what maybe what will be the final temperature, or what must you add to the system for such and such to occur. And what we found was there's two major players when trying to work out a problem like that. The first is specific heat, which is basically how much energy would be required to add to an object, a material, in order to change its temperature. The second is how much energy would you have to give to a material, or how much energy would that material give away if all it wants to do for a particular time is change the state of matter. And so, for instance, if you put ice in some hot water, the hot water is going to cool down. That's the CM delta T type thing. The ice goes through multiple phases. First of all, you have to heat up the ice to the melting point. That's CM delta T. Then the ice can melt. That's the latent heat. And then once it's melted, that melted ice can now change temperature as well. So that's another CM delta T. So those are the two big phenomena you need for calorimetry. First, specific heat, changing temperature, and the other latent heat, which is changing phase. Now, today what we're going to start is a different area of thermodynamics. It still deals with heat, and in fact, what this is called heat transfer methods. So obviously, when we talked about calorimetry, we just took for granted the fact that heat, energy, can be transferred from one object to another. Now, it's fine to assume it because we see it in our everyday lives, of course. If you put some ice in hot water, we see that the energy from the hot water gets transferred into the ice, cooling the water, heating up the ice. However, what we now want to do is dive a little deeper into that and discuss how physically this energy can be transferred from one object to another. And in fact, what we see is there's really three methods that we're going to discuss. Okay, the first is called conduction. Conduction is a method of heat transfer. So this is, you're going to have two objects and you want the hot object to give energy to the cold object. And it always works in that direction. That object which is hotter will always give away energy. A cold object does not give its energy to a warm object. That's the opposite of what happens. Now, this particular method called conduction is a method whereby that heat is transferred because of physical contact. So you're literally touching the two objects together. Okay, so one thing you can imagine is you put a hot pan of cookies in the oven to bake, and then you go to take the pan out, but you forget to have an oven mitt or a towel or something, and you go touch the pan, and of course it's hot and you burn your fingers. That's heat conduction. When your fingers touch the pan is at a higher temperature than your skin, and so energy will flow from the hotter object into the colder object, and that causes a burn. That's heat conduction. two things actually physically touching can transfer heat between themselves. The next method is called convection. Now, this is not quite as straightforward to picture, but this is basically heat transferred because of the motion of its environment. Now, there's a couple of examples we can use for this. The first is the sun. The sun is, of course, a big ball of gas, hydrogen gas, and others, helium and other things, that's undergoing a bunch of nuclear reactions. And that's why it's hot, and that's why it burns, and that's why it gives off light. Now, the nuclear reactions are happening near the core, near the center of the sun. And so it's much hotter there than it is at the surface. As you progress from the core to the surface, the material of the sun, the gas, is cooling off. However, what happens, because some areas are cooler and other areas are hotter, you get this kind of boiling or mixing around of the material. The gas acts kind of like a fluid, and it flows between itself, moving the hotter parts of the gas to the colder areas of the gas. And you kind of get this mixture where the heat can be moved from one area to another. Another one, which is a little bit more clear, at least to our everyday lives, is if you ever heard of something called a convection oven. And a convection oven, what you have, well, first of all, a basic oven. Basic oven, you put your cookies in the oven. There's, if it's an electric oven, you have heating elements. Those heating elements get really hot, and that heat makes the basically box, which is all the of it is, get really hot. The air inside is very hot, and so you put your cookies in there and they bake. Now, what generally happens, of course, is ovens are not perfectly balanced, and you'll get hot spots. One oven may have the right side of the oven is hotter than the left side, or maybe the back left corner is hotter than the front right corner, or whatever. And so usually what you do is you rotate the pan halfway through cooking so that you get even baking. You don't have the left side of your pan of cookies much more overcooked than the right side of your pan of cookies. That's a regular oven. Now, what people did was they said, look, we want to try to mitigate this heat imbalance as much as possible so you don't have to rotate the pans. And so they thought about putting a fan inside of the oven that'll blow the hot air around to make sure that the hot air is equally placed in all locations of the oven. So if, let's say, the right side of the oven would have been the hotter side, by placing a fan that's blowing the air around, that super hot part on the right side is now able to move around all parts of the oven. And so you get more even baking. That's convection. You're moving the hot air around instead of letting it just sit there as it is and placing an object in that hot air. So that's convection. The last method is going to be called radiation. And radiation is a method of heat transfer that we're all used to. In fact, again, if we go back to the sun, when you go outside in the daytime, of course, today is not a good day to think about it because it's really cold out there, but on a normal day, you walk outside and you feel the heat from the sun. Now, how is this possible? You're not touching the sun. The sun is 93 million miles away. But yet you feel the heat coming off of the sun. And the reason is because what is going on with any object that gets really, really hot, or for instance, if you think about putting your charcoal You put charcoal in a barbecue pit, you light it on fire, it heats up, and then it starts to glow red. Or if you have an electric stove that has those little circular heating elements, you turn it on high, that circular heating element will glow red or orange. But what's happening is as you feed this material energy, you energize it, you get it excited. The atoms, which make up the material, have a bunch of electrons flowing around. So if I were to draw a little picture, here's the nucleus, and the nucleus has these little electrons rotating around, of course. And if you feed in a bunch of energy into the system, then that energy will be absorbed by these electrons, moving them to a higher energy state. So the electron will move up to a higher, let's say, orbital, if we're going to be chemists about it, and will now orbit the atom at a higher energy level. So it's excited, it's in an excited state. However, naturally, these electrons don't like to be in an excited state. They're lazy. They want to be in the lowest energy state they could possibly be. So what will happen is after some period of time, it's going to get rid of its excess energy and drop back down to the lower energy state. But in doing so, it gets rid of its energy in the form of what's called a photon. And the symbol for a photon is the gamma, the Greek letter gamma. And what a photon is what's called a particle of light. And so it gives off this energy as light. And of course, what we know about light is that light comes in a whole bunch of different colors, the whole spectrum of frequencies. And there's a certain range of frequencies that is what we call visible light. That is, we can see it with our eyeballs. Our eyeballs have the ability to recognize that frequency range. But of course, it doesn't have to be in the visible light. It could be at any frequency of light. But if it just so happens to be high enough energy, then it's visible to our eyes, and that's why we see the thing glowing red, because the electrons are sending out energy, sending out light, whose frequency, whose energy is high enough to be that of the red visible light that our eyes can see. But like I said, it doesn't have to be in the visible light. It could be lower energy, in which it'd be infrared, let's say, or it could be higher energy, ultraviolet, which is what gives you a sunburn from the sun. But either way, this light is radiating from the electrons in the atoms. And we can feel it. And the way we feel it is as heat, especially infrared light. That's why, if you've ever seen like the Predator or these infrared goggles or heat-seeking cameras or whatever, where you could see the temperature of objects based on the color that the camera is showing. What that's doing is just detecting light in the infrared spectrum, which is where heat, the majority of heat takes place. So that's what radiation is. Radiation is the transfer of this energy by means of sending out light, sending out energy that we detect and we feel. Okay. So that's the three ways. And of course, if you ever light a fireplace or you go camping or whatever, and you feel the heat from a fire, that's radiation. You're not touching the fire, that would be conduction, but rather it's the radiation. It is the heat, the energy being sent away from the material because the electrons are moving around in their orbits. So those are the three types of ways heat can be transferred from one object to another. What we're going to discuss in this course are two of them. We're going to discuss conduction and radiation. In fact, we're going to get equations for these two methods so that we can do some calculations and predict what's going to happen. So the first one we'll do is conduction. That's what we're going to talk about today. Heat transfer through by conduction.
Excuse me, Dr. Rysmith.
Yeah, what's up?
I just wanted to get a clarification. The example that you said for radiation will be feeling the heat of fire.
Yeah, that's one example for sure. Yeah,
Okay.
or a hot cup of coffee and you put your hands over the mug of coffee, you could feel the heat coming off of it. That's a form of radiation. That's right.
So convection is like, let's say you have to move or give some type of energy to generate heat, or is that what you're trying to say for convection?
Convection is a little bit more awkward, but what I would say about convection is, imagine you have a box, and inside the box you have some hot air. Now the hot air may not be completely balanced all over the place. You may have hot spots and cold spots. Well, that's fine. However, if you start then allowing that air to move around. So for instance, if we have the box of hot air and we put something in it and the air doesn't move, well, eventually all that's going to happen is the air that's touching the surface of the object you placed in there will give its energy to the material, but then that little layer of air that's sitting right on the surface is eventually going to come into equilibrium. But the rest of the air is still hotter, and it's not going to give any energy away because it's not touching the material. However, if that air then is allowed to move through the material or around the material, then eventually all parts of the air will come in contact with the material and give away their energy. So with convection, the big point about convection is kind of the motion, whether it's a natural motion like the sun, the fact that you have really, really hot parts of gas and really cold parts of gas, it's turbulent and the gas swirls around itself simply because of the different temperatures. Or in an oven where you literally have a fan to force the air to move, it is that motion of the fluid, gas or liquid, let's say, that is what we consider to be convection. Okay, so it's not as straightforward as, let's say, conduction, where you say, oh, conduction, that's easy. You touch an object, when you're in physical contact, energy transferred between the objects. Convection's a little bit more abstract, but deep down, what you want to think about with convection is the motion of the fluid, the thing which is hot, trying to give away its energy. It's the motion of that fluid around the object which gives rise to the energy transfer. Okay, so is that a little more clear?
Yes, sir.
All right, cool. So conduction. One way we're going to talk about conduction, or the main equation, what it allows you to figure out is how much heat will be transferred from one object to another per second. And this is what's called the heat transfer rate. So it's like, how fast does the energy move from one object to another? If there's a really high heat transfer rate, then a whole bunch of energy flows per second. And if it's a really low heat transfer rate, then obviously very little heat goes per second. And so what the equation says is Q over T. So that's how much heat per second. The amount of energy per time is given by a constant called K, and this K is called the conductivity. Conductivity, like specific heat, is a number associated with a particular material. So each material has its own conductivity. And what it describes is how easily does heat move through the material. So for instance, if you have something like a metal, well, metal allows heat to move through very, very easily. So it's a very high conductive material. Whereas if you have something like styrofoam, well, heat has a lot of trouble trying to get through styrofoam. And so it's got a very low conductivity. So a whole bunch of materials have a whole bunch of different conductivities. This is a number that's usually given in the problem. You know, oh, this, the conductivity of this glass is 500 joule, and I believe the units are going to be joules per second Kelvin, if you want the units. Okay, so it describes how much heat can flow per second due to the temperature that we're talking about. So that's conductivity times how big of an area do you have to allow the energy to flow through. So this is called the surface area, A, surface area. And this you think about, let's say we're talking about like a window. Here's a window. And outside, it's really cold right now. Inside, hopefully, inside your house or your apartment, it's warm. And you say, well, I want to know, usually windows are where a lot of heat can transfer from one area to another. I want to know how much heat is going to flow through my window from my room into the outside environment. So like if you have your heater on in your house and it's really cold outside, well, the reason you have to keep having the heater turn on and on and on is because eventually the heat that's inside your room transfers through the window to the outside, cooling down your room. And so your heater has to turn back on again. Well, obviously, if you have a really, really big window, then there's a whole lot of area where the heat can flow through the window. Whereas if you have a little bitty window, then there's only so much area there where heat can go through. So a much bigger area, way more energy can flow through than a smaller area. And so that's why it depends on the surface area. Then there's a term, delta T, where delta T in this case does not mean the change in temperature, but rather the difference in temperature. And of course, what I mean here is, just like I said, inside your room, it's 75 degrees Fahrenheit. Outside, it may be 35 degrees Fahrenheit. So there's a big difference in temperature. And because there's a big difference in temperature, that energy really, really wants to leave to the colder area. Whereas if it's 75 inside and 75 out, or 73 outside, there's not really that big of a difference in temperature. And so the energy isn't really, really trying to escape. It's just kind of leisurely leaving. So this heat transfer rate should depend on how big of a difference in temperature there is between the two ends of your material. And then lastly, the last term is L, but of course, if I write L, it looks like a 1, so I'll do it in script, L. And L is the thickness of your material. So of course, if we're talking about glass in a window, if you have a super, super thick piece of glass, then it's really difficult for energy to try to flow through all of the glass. But if you have a really thin piece of glass, the energy can get through it fairly easily. Another way to think about it is if you walk outside and you have a really thick coat, You stay a lot warmer than if you walk outside and you just have a thin t-shirt on. The thin t-shirt, the energy can flow from your body to the outside fairly easily, whereas a thick coat, the energy can't make it through all the material, so you're insulated. You keep the heat next to you. And that's the equation. For conduction, the amount of heat that flows per second, the heat transfer rate, is given by the conductivity, how easily does the heat flow, times the surface area of the material you're trying to pass the energy through. A bigger piece of material, more spaces for energy to try to get through. Delta T, if there's a big difference in temperature, it's really hot and really cold on the other side, then it's like that energy really is getting forced through the material very quickly. If the temperature difference is very small, then there's not a big force trying to push the energy through, so it doesn't go through quite as fast. And of course, the thickness. The thicker the material, the harder it is for energy to flow, and so you should get less energy per second moving through. That's why it's in the denominator. So there's our equation. That's what we're going to use for conduction. Now, what does a typical problem look like? How will we use this particular equation? So the example, let's say we do this. We'll say, you have a window whose conductivity is, let's say, 200 joules per second Kelvin. The window measures 1 meter by 2 meters. Okay. It has a thickness of 20 centimeters. If the inside of the room is at 25 degrees Celsius, and the outside is at 5 degrees Celsius, calculate the heat transfer rate through the window.
I got a question. Is that 1 times 2 meters is what you're saying, or?
Yeah, it's 1 meter by 2 meters. So, if you have a window, let's say it's 1 meter wide and 2 meters tall, basically.
Okay.
So basically, all this is a way for you to calculate the area. But instead of just giving you the area, I'm giving you the dimensions of the window.
And that's 20, the 20 is 20 centimeters, or?
That's right, centimeters.
Okay.
Mhm. And so there's my question. Now, the way I'm going to show this, usually for these types of problems, what we want to picture in our image is we're going to look at the edge of the window. So a side view.
Could you
Yeah.
scroll up real quick?
Sure. There you go.
Okay, thank you.
So when I draw these pictures, and you're going to see why in later examples, it becomes more important. But instead of drawing the window front on, like I'm looking at the face of the window, I'm going to look at the edge of the window instead. And so if I draw it, it's going to look like this. Okay, so there's the edge. So this is like the thickness this way. Okay. And the inside of my room will be at a temperature of 25, and the outside will be at 5 degrees. So here's the inside of my room, and there's the outside of my room. So the heat is trying to flow through this particular piece of window. Now, I want to calculate the heat transfer rate. And all that means is I'm using my equation to solve for Q over T. That's called the heat transfer rate. All right, well, the equation, of course, Q over T is conductivity times area times the difference in temperature over thickness. So pretty straightforward. We're given all the data in my problem, plug all the numbers in, calculate my answer. No big deal. So conductivity, I'm told this window has a conductivity of 200. Area, I need the surface area of my window, and I'm told it's a 1 meter by 2 meter window. So I just multiply 1 times 2. That gives me an area of 2 meters squared. Then we have delta T. Now, delta T does not mean final minus initial. There is no final temperature and initial temperature here. You're not changing temperatures. Rather, this is the temperature on one side and the temperature on the other side. So I'm going to call it T1 and T2. Okay. So I'm going to call T2 the temperature inside my room, and T1 will be the temperature outside my room. Now, I could do it the other way. There's no problem saying the inside temperature is 1, the outside temperature is 2. It doesn't matter. You'll see what happens when I get an answer if you did it the other way. But for now, this is what I'm going to label them. And so what delta T means is T2 minus T1, the difference in temperatures. So for me, the inside, 25, minus the outside of 5. And then all of this is divided by the thickness, and I'm told this window has a thickness of 20 centimeters. Of course, centimeters is bad units. We have to convert to meters, and so this is actually 0.2 meters. And there we go.
T1 and T2 labeled as again?
Yeah, so I have T2 is my inside temperature, 25 degrees, and I labeled T1 is the outside temperature. In this case, of course, I could have called the inside temperature T1. It's just a name. It doesn't matter what you call it. But what the reason I'm labeling it this way is because notice what would happen if here I labeled it the other way. It would be 5 minus 25 instead. Well, 5 minus 25 is a negative number. So the answer I would be getting if I labeled it the other way is going to be a negative answer. But what I'm asking for is the heat transfer rate. A certain amount of heat is going to flow per second. It doesn't make sense to have a negative transfer rate. Like if I said, how fast are you going? You don't say negative 35. You say, I'm going 35 miles per hour. Now you may be moving to the left. So if I wanted your velocity, you'd say negative because to the left is negative. But if I just want your speed, how fast are you going? You don't care about positives or negatives. Same thing here. When I ask for the heat transfer rate, I should get a positive number. A certain amount of energy will flow per second. Now, positive and negative may tell you, is it flowing outside or is it flowing inside? But that's not what's being asked, so it doesn't matter. So all of that is to say, if you labeled T1 25 and T2 5, then whenever you get your answer, if it happens to be a negative number, just make it a positive number. There's no problem with that. But anyway, there's all my numbers just sitting there. So all I have to do is multiply all this stuff out. So 200 times 2 times 25 minus 5 is 20. All of that divided by 0.2 gives me an answer of 40,000 joules per second. That's how much energy will flow through this one window every second, 40,000 joules. So any questions about this particular example?
So Q over T is like the whole thing that the conduction is equal to, like they're not two separate variables.
Well, yeah, so here's the thing. It's a very good question you're asking. And the answer is more complicated than your question. Number one, Q means energy, right? That's how much energy flows. T means time. So it is two different things. Okay, Q is energy, T is time. They're different variables. However, what we have done is we said, look, sometimes I don't care what the energy is. What I care about is how fast the energy will move. Kind of like saying, here's something completely separate, but the same basic thing. We have distance and we have time, right? You could say, hey, I went 50 miles and it took me 1 hour to do it. Okay, that's fine. I don't really care how far you went. I don't care about that. What I want to know is how fast are you moving? Well, it turns out that the distance you traveled divided by how long it took to do it is the velocity. So what your question asking me just now is the same as saying, is X over T one thing or is it two different things? And of course, the answer is it's both. It's a distance and a time, so it's two different things. However, when we take them together as X divided by T, we call that thing velocity, which is its own separate entity. So just like that, this Q over T business is on the one hand saying how much energy divided by how long does it take for that amount of energy to flow. Two separate quantities. But if I take it as one thing, if I solve for that thing, I can also call it the heat transfer rate. It's like the velocity of the heat. Okay, so a little bit of a complicated answer, but I hope it makes more sense to you. Is that all right?
Yes.
Now, with that, however, it does bring me to exactly the next thing I was about to say, which is I can ask a part B to this question. I can say, okay, now that you know the heat transfer rate, I want to know how much heat will flow through this window in 3 hours. Now I have something different. Now I don't care about the heat transfer rate per se. Rather, I'm telling you, we're going to wait 3 hours and we're going to collect all the energy that's going to move through. I want to know how much energy is that going to be. Well, now you say, aha, I solved for Q over T, and that was 40,000. That's what I did in part A. However, what I want here is Q. I want how much heat, how much energy. So move the T over to the other side. You get the total energy is going to be the heat transfer rate, 40,000, times how long am I waiting? Well, in this case, I'm going to wait 3 hours. Now, hours is a bad unit. Remember, in physics, we're always using seconds. So I have to convert 3 hours to seconds. So I multiply by 3,600 seconds in an hour. So I get 3,600 times 3 is 10800 seconds. And so I say, aha, 40,000 times the amount of seconds I have to wait, 10,800. And this will tell me my total amount of energy which will flow, which is 432 million joules. And so here we've taken what was its own quantity, heat transfer rate, and we've broken it up into its separate pieces. One of the pieces is the total amount of energy that flows. The other piece is how long did it take that energy to flow? In this case, I want to know how much heat, how much energy. Well, you better tell me how long we're waiting because all I have is the heat transfer rate. Now, this is one way to solve the problem. But let's say you're on a test and I gave you this problem just like this, except instead of part A and B, I never asked you part A. All I asked you was part B. Well, you can, number one, solve it just like we did here. First, you calculate the heat transfer rate, get a number. Then once you know the heat transfer rate, you then solve for Q to get the total energy. That's one way to do it. We just did it. But if I don't need part A, why waste my time calculating part A? On a test, you have a certain amount of time to take the test, and you don't want to waste it on doing things you don't have to do. So I'll show you a second way to do it where you could get the answer straight up. Notice the equation is Q over T is Ka delta T over L. Well, what my problem is asking me is, given all the information, how much heat will flow? That means solve for Q. So all I have to do is just move the T over to the other side and I get a new equation, Ka delta T over L times T. So I could have plugged everything in at the very beginning. I could have said, okay, the conductivity was 200. The area was 2. Delta T, 25 minus 5. The length of time I'm waiting, 10800. All divided by the thickness of 0.2. And that just gives me the Q all by itself. And I don't have to solve for Q over T first. Okay, so this is what's important to realize about the equation. And it gets to the heart of your question, what you just asked. That is, given an equation in physics, generally speaking, it may be set up in a form to solve for a particular thing. Like in this case, the conduction equation solves for heat transfer rate. But each part of that equation stands for something. There's conductivity, there's the area, there's the thickness, there's the amount of heat, there's the time. Each thing is its own physical representation. So what you're going to have to do is, as you read the problem stated, given to you, look at what it is it's asking for. And then take your equation and solve the equation for the thing you're trying to solve for. Just because you set it up as Q over T doesn't mean you have to solve it as Q over T. I can manipulate it and solve for the time. I could have asked, okay, given all this information, how long do you have to wait for 50,000 joules of energy to flow? Well, in that case, I'd be looking for T, little t. I'd know Q, 50,000 joules. I'd know the area, the conductivity, blah, blah, blah. And I'm solving for time. However, in this particular example, the very first thing I asked about was the heat transfer rate. And when you see heat transfer rate in your mind, it's Q over T as a quantity. It could be, I want the energy, in which case you solve for Q. Move the T over to the other side. Or I may be asking, what's the temperature on the other side of the window if blah, 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 blah is true? Well, then you're solving for one of the temperatures and so on. So are there any questions about the theory for this type of problem? The good news is this is the only equation you have for conduction. Obviously, we can manipulate the equation and solve for different things, but it's just this equation. What we're going to do next class is continue with it, because an interesting problem we want to get into is, what if we have a situation where instead of just having a window, what if we have two different materials? So maybe you have something like a wall and a painting that's on the wall, and heat wants to flow through that system. And so I tell you information about the painting, I tell you information about the wall, and I want to know, what's the heat transfer rate through this system? Well, now it's a little different, because it's not straightforward how to take this one equation sitting here and deal with the fact that you have two separate materials, two different conductivities, two different thicknesses. Maybe the areas are the same, maybe they're not. And so what we want to try to figure out how to do is have a system with multiple layers, try to send heat through that system, and see how can we calculate the heat transfer rate through a compound system. That's what we're going to do next time. I will foreshadow and say it's still this equation, but we may have to use it multiple times. And we may get stuff like two equations, two unknowns, or the like. We'll see. But we're not going to have a separate equation to have to work with. Anytime you see conduction, it's going to be this equation. All right, so that's all I have for this. Just reminders, I posted on Canvas the second homework for calorimetry, which of course this problem has latent heat in it. And so that's due, I think I have it due Monday by midnight. I didn't want to have it due too much later, just because since we move on to a new topic, I don't want to have confusion between the topics. But it's only one question, so it should be fairly quick to solve it out. So certainly work on it as soon as you can, just to get it out of your hair. But it's due Monday by 11:59 p.m. as usual. So look out for that. Also, keep checking Canvas, because I am uploading the recordings from Zoom on there, as well as these kind of whiteboard sheets that we're going through. I call them lecture notes, but they're not really notes. They're just what we wrote on the board, so that you can download them if you want to have them to look back at how I was solving stuff and the like when you're studying. So all that stuff's available. I also have last year's recordings on heat conduction and examples for heat conduction for you to be able to watch if you want as well. So a bunch of stuff is updated on Canvas, so make use of it if you wish, but certainly make sure you work on the homework. Do it today so you don't have to worry about it over the weekend, because it's from the last class's material. So other than that, if you have no questions, you're free to go and enjoy your weekend.
Thank you, you too.
All right, see y'all later.